This is conceptuality video 15c. In the last one, we showed you this construction, and you should recognize it. I mean, we just talked about it, showing you that the tetrahedron on top of the tetrahedron here in the tetrastar concept. You know, so that there's two tetrastars, this black one and the red one. Okay, in the writing we referred to the tetrahelix coming off of those two of that construction, which is existent in here, right inside this cube, right? I mean, as we've talked about. I know this is difficult to see, and it's not necessary to understand it totally in terms of detail. It's the detail can be verified, but it's the generalizations that we're interested in, and the thematic considerations that can organize thinking. It's up to experts in every field to use this tool however they will, if they want to. But anyway, here's the tetrahelix. Oops, this one is broken. But here's that tetrahelix coming off of those two tetrahedrons that we discussed in the writing, and I didn't show you a visual for that. Okay. Now we want to talk about the other fields that are potential that are other field concepts, right? That are congruent, or they fit in with the octet. I mean, it's all based in the same thing, but there's other ways to look at the fields, other possibilities of perspectives on the very same field that we've been studying. In this case, you can see the cube here, right? Which we're using because it's easy for everyone to visualize. You don't get lost visually when you start with the cube. This cube is the square root of 2, right? And you can imagine that to be in the octet matrix that we've just discussed. It would just be the matrix as we've discussed it and studied it inside that cube. Now, in this case, we've analyzed it differently. That we have thought about putting an octahedron on interpenetrating this cube. So we know that the diagonal across the cube is the square root of 6, right? And we know that if we put a half octahedron on here of the square root, with each one of these being half the square root of 6, and we push it in, we have it in here, right? So this makes an octahedron. Here's the 4 top vectors, and here's the 4 bottom vectors of an octahedron that has the dimensions of 1/2 the square root of 6 there, and the square root of 2 here. Now that creates the dodecahedron, which is an all-space filler, because you can imagine another cube sitting right here with this interfacing the cube and this cube going this way, and that you could have a cubic field that's completely rational with this construction. This is an all-space filler. It's a one concept, a one octahedral concept as an all-space filler. It doesn't require the octet complementarity in purest principle. So now, in the case of this field, this right here is the octahedron that surrounds this, right? And this octahedron, if this is square root of 2, this is half the square root of 6, this dimension across here has to be 2. And so this is a 2-frequency octahedron here, right? Now, it's interesting that when we do the implosion, the tetrastar implosion, we get a 5-frequency surrounding octahedron. And really, that's the first truly easy to see and rational way to look at all of this, with coming up with even number proportionality. The proportionality is still the same in principle, no matter how you do it. But if there's you run up against a problem conceptually until you get to the 5 frequency. It's all still true, but it doesn't come out in rational whole numbers. I think there's a message in that about going below below the atomic concept. If you start looking at subatomics, the problem that you run into conceptually is somewhat indicated thematically in what I'm trying to talk about here. So, for example, this is a 3-frequency octahedron, and the cube that is formed by the intersection of the points in the center of each octahedral face comes out to be, in this case, square root of 2. And then the octet reality inside that cube, becomes unit dimension. But this is the big cube. You know, it should be, in order to get unit dimension on the small cube that we've talked about and explained conceptually, you would have to have, this would have to be an F5, a frequency 5. So you see here that we're running into a kind of a conceptual, just, take a step and look at this. So that I think that that there's a message in that. But anyway, so this is the this is frequency 2 octahedron. This is frequency 3 octahedron with its messages, and this is the frequency 5 octahedron. Or it can be the 15, or it can be the 30, or the 45, and all of these things, all of these dimensions come out as whole number square roots. Or yes. So now there's one more field that is just fascinating that I want to show you, and it's so, it's really beautiful. This is made up of it's really octets, and I don't want to get into all of it. Because it's more fun to just investigate it yourself if you have an interest in this way. In the field theory. Like I said, in the whole overall conceptuality, you don't need to understand it in detail, but I just want to touch on it because it's so beautiful. This field is the hexagonal field, and you can see it's only made up of this one tetrahedron right here. This tetrahedron is based on the triangle in the middle, which I'll show you in this construction in a second. But this becomes 1/2 the square root of 5, and this is 1. This is 1/2 the square root of 5, 1/2 the square root of 5, 1/2 the square root of 5, 1 and 1. That's all there is to this tetrahedron. But when you look at it like this, it turns into an equilateral triangle. This square root of 5 flattens out to be 1, right? Because you see an equilateral triangle here. This is a simple indication of how theoretical physicists are talking about holographic reality, that really it's perceptual. That when you look at this, you see it's flat, but you can also see it as this, right? So here is that tetrahedron right here in this construction. And you can see that 6 of them make a perfect hexagon. This is 1, this is 1/2 the square root of 5, this is the square root of 3. And that's the only dimensions involved in this matrix. And this matrix creates some beautiful and interesting geometries that are really simple. For example, this is 1. This is square root of 3. Across here would be 2. It's such a simple matrix, but it achieves a rational understanding of the hexagonal crystal system. You can imagine how being polarized like this, it could stack into a hexagonal prism, like a quartz crystal. So, but it can manifest, because it has this flatness aspect to it. It can manifest as a snowflake, right? So it's a really beautiful common ground for that understanding. Also, like this, let's see, what can you see? You see this kind of lenticular, this triangular thing. That's exactly the same triangle, the same lenticular space as this larger space, so that it has that regressive and progressive capability also, which could, and implies the complexity of a snowflake. So anyway, that's really what I just wanted to introduce, and I think that those fields could be studied, by mathematicians in more depth, and come up with some really usefulness. So that's it.